and welcome to this video. In this video we're going to go through diffraction in a little bit more detail than we did in the introduction video. So hopefully by now we should be happy with the general idea of what diffraction is. It's when we put light through a slit, whether that be a single slit, a double slit, or a diffraction grating, and we see some kind of interference pattern, and how we see that is going to change depending on whether it's single slit, double slit, or a diffraction grating. And we know the reason that these the fringes and the interference pattern forms is because of that path difference that we were talking about between the two slits, or in the diffraction grating it would be between two adjacent slits, but we never really understood why the single slit still did this, and we said that it was due to a thing called Huygens principle, but we never really explained it. So let's start off by explaining what Huygens principle is, and this is what's going to allow us to narrow it down and try and get to some equations that is going to explain most of this diffraction stuff for us. So Huygens principle, Huygens was the first person to really say that light was a wave. Originally Newton assumed that it was a particle, and Huygens proved him wrong by using this idea that diffraction is a property of waves that can't be described by the particle model. But Huygens' principle basically states that any source of light can be split into secondary sources. So what is happening in this slit here is that this is currently if I draw it a little bit bigger, so it shows, imagine this is a zoomed in image of the slit. We have multiple different secondary sources. Each of these things are emitting their own version of this that is going to interfere with each other. Then as soon as we have each of these, at the edge of each of these we have even more secondary wavelets, okay, and these will each emit their own. So this is the general idea of Huygens principle. Obviously this diagram is not accurate at all, but you get the general idea that we can treat this slit as being a source of many different secondary or we can treat the slit as being the basis of sources for all of this light that's coming out. And this is why we get this overlap. And if you remember, this looks very similar to what we saw in the double slit, where we can have these positions are where the waves overlap and interfere, and then we'll get some sort of diffraction pattern at the end. So this is Huygens' principle. How does that help? Well, we can now look at that in the case of a double slit. Okay, this acts as one wave source, this acts as another, and we have this kind of curving effect again. Each of these has its own source of waves, so we could have actually just done this and split it up into these and each of these, and then we'd get an overall thing. That was how this was originally proven. Proving it now is going to be a little bit simpler than that actually, because we have this idea. So let me draw a bigger diagram here, but we have this idea already that if the path difference, so for a fringe to be made, for a maxima to be formed, the path difference must be an integer number of wavelengths. Okay, now we're going to assume a few things about this idea here. So we're going to say that the central maxima is going to be here, and we're going to have the first maxima, so where n is equal to 1 here, this is n is equal to 0. This is going to give us the starting point of this equation. So we're going to say that the light from here need only go directly across. Okay, so it means that this light only travels the distance between this slit and this screen, which we're going to call capital D. Okay, we're going to say the distance between these two slits here is lowercase d. Okay, because it's a much smaller distance. Uppercase d will usually be on the order of a few meters, whereas lowercase d can be a couple hundred nanometers. It doesn't really play that much of a role, but the second ray is going to come in and is going to constructively interfere there to form that maxima. This angle here is going to allow us to do some calculation now. So if we know that this total distance is d, we know that some of this distance is d, and then we have some extra distance. To quantize that, we're going to introduce something called the small angle approximation. Okay, so the small angle approximation, if we were to think about it, I'm just going to call it small angle approx. If we were to have a right angle triangle like this, and we were to look at the distance that this hypotenuse is against this adjacent here, as we keep decreasing this angle of theta, the distances, or the difference in the distances, is going to get smaller and smaller. So if we have an angle here that is incredibly small, then we can approximate that the distance across here is going to be the same as the distance here. Okay, so let's make this into a right angle triangle just by doing this. And this allows us to say that if this distance across here, so this is the right angle here, if this distance across here is capital D, then this distance from here onwards is also capital D, okay, using this small angle approximation. Now, that means that this distance here is going to be some extra displacement, okay? This is some path difference, and this is what we want to work out, because we need to make sure that for this to be a maximum here, this path difference needs to be an integer number of wavelengths. So now we can apply some more trigonometry, because we can say that if this angle here is theta, then this angle here is going to be 90 minus theta, which means this is a right angle here, so this angle here is also theta. Okay, so this angle here is theta, and this length is what we're trying to work out. Now, to work out what this length is, given that we know the angle and we know this side, and this side D is the hypotenuse, we have a new triangle. So let me draw that triangle here. I'm going to draw it slightly differently to the way, to the orientation it has in the diagram. But this angle here is theta, this bottom here is delta S, and this hypotenuse is D. This is an opposite and a hypotenuse, so we're going to have a sine of theta is equal to the opposite delta S divided by the hypotenuse, which is D. Now we can rearrange this and say that delta S must be equal to D multiplied by sine theta, and we know delta S has to be equal to an integer number of wavelengths, so that means that D multiplied by sine theta must be equal to n times lambda, and this is one of the equations on your formula sheet. Okay, it's a pretty simple derivation. It's not using any complicated geometry or maths or anything like that. This value of n, you'll notice that I've been labeling these maximas as n. And so this is what this value of n means. This n is the order of maxima, which is basically saying that between, so to get to n equals 0, to the central maxima, there is 0 path difference, because it is exactly in the center of both of these slits. Okay, to get to n equals 1, then this length here has to be 1 wavelength larger than this slit screen difference. To get to n equals 2, the path difference between them is going to have to be 2 wavelengths, and so on. Okay, so we can have this in both directions. Okay, what this is going to allow us to do is, if we know generally which maxima we want to look at, we can then look at what the angles are going to be to get to there. We can also use this to find out how many maxima can we actually see. This is a common exam question. So we can, let's scroll down from this and let's answer the question, how many maxima are formed? Okay, and we can answer that question using this equation. So we can say, for example, let me just get rid of these lines. We can say that we know that the maximum angle that it can change is going to be 90 degrees, okay? Because if we have some sort of double slit and the angle between that is going to be this angle here, the maximum that angle can be is 90 degrees. We can't ever have something reflecting off of thin air, okay? Unless it's a sound wave in an open-ended tube. But we can't have light reflecting off of thin air. So what's going to happen is we can set the maximum value of n is going to occur when we have this maximum value for theta. And the maximum value for theta is 90, which means the maximum value of n occurs when sine of theta is equal to 1. Since sine of 90 is equal to 1, this means that n is just going to be d over lambda. Okay, that's the maximum amount of things we can get. Okay, you'll notice now the more maxima we have will be based on the difference between these two distances. The maximum value we can have is when they're the same. Okay, so when they're the same, so when, and we'll prove this again using the second equation, so when the distance, the slit distance is the same as the wavelength, this is when we get the maximum amount of diffraction. Okay, so this is when the maxima that we see will spread out the most. We get the maximum amount of diffraction. Okay, there's an important point here, so I'm not going to put any values in because I've found from experience that when you put values in, you tend to get incredibly weird numbers. You should get normal numbers. It tends to be when I make up numbers, they tend to be weird. So what we have to find out here is this is the biggest order on one side of this central maxima. Okay, so we'll have a center here that's n equals 0. What we're finding is the biggest n that we can get on this side. That's not going to tell us how many maxima are formed because we can have that whole thing reflected onto the other side. So we have to take n, times it by 2, and then add the central maxima because this isn't including n equals 0. So we have to take the biggest number, times it by 2, and then add 1, which means if we were to put this into this, then the amount, this could be an equation if you wanted it to be, is just going to be 2d over lambda plus 1. This is the maximum amount. I'm not going to put a box around it because it's not on your formula sheet. You don't really need to know that equation as long as you can recognize that your maximum number, your maximum order of the reactant, or the maximum order of diffraction is going to be when theta is equal to 90, meaning that that's when d over lambda is the biggest, and so then we can get a reflection, and then we have to add the one in the middle. And this equation can be used for this. It's also used quite commonly for diffraction gratings. So in your formula sheet, this is the equation that is labeled diffraction grating. We've used a double slit to derive it, but it is also applicable to diffraction gratings. It would also technically be applicable to single slit diffraction, but we tend to only use it for diffraction gratings because it's much more accurate that way, because of the small angle approximation we've had to make to form it. This isn't the only equation you have to know though. I'm not going to derive this second equation. If you wanted to, it's not too complicated, but since this derivation you can be asked to derive, but the other one you're not going to be asked to derive, I'm just going to leave it out for now. I'm sure there's plenty of resources that will go through it, but because it's not completely necessary, we'll just leave that for this video. So the other equation is looking at this idea of fringe spacing. Okay, now fringe spacing we're going to refer to as W. Okay, this is just the letter we give it, because all of the distances and displacements and everything is D and S, and everything's already been taken. So fringe spacing we refer to as W, and the equation is that W is lambda times D over S. Okay, this is on your formula sheet, where W is the fringe spacing, which is a distance, so that's meters. Lambda is obviously wavelength, also in meters, and D is what we call the slit to screen distance. So the big distance, we've always referred to this as D, but S is now the slit spacing. Okay, this can get very confusing. It's also in meters. This can get confusing because up till this point we've referred to D, to the slit spacing, as being lowercase d. So there's a fine confusion. So lowercase d and lowercase s represent the same value. Okay, so these are both the slit spacing. The reason we have a difference in the letter that we have is basically just because two different people formed the equations, and that was their convention. In physics, we just name, if we have a distance, we can name it whatever you want. And so because the person who derived fringe spacing named it as S, it's S. So just don't get too confused about that. It's literally the same distance, we just have a different letter for it. But what this tells us is the relationship between, so if I have all of these fringes on the screen, the distance between these two is W. Okay, this, you'll notice that this doesn't depend on n. So it doesn't depend on how far away from the central maxima you are. They should all be the same. They should all be the exact same distance. So all of the differences should all be equal to W. And you'll see that this is only dependent on the wavelength of light that we have, the distance to the screen, and the slit spacing here. The common thing that they can ask with this equation is mostly, if we make this change, what happens to this? So they might say, if the wavelength is decreased, what happens to the fringe spacing? What happens to W? Now we've already answered this, but we can use this equation to prove the same thing. If lambda is equal to S, the slit spacing, that's when we have the maximum amount of diffraction, because that means that if lambda is equal to S, we can cancel those two out, and the fringe spacing is going to be the whole distance between the slit and the screen, and that's going to be a few meters, which means we're going way bigger. So in general, the slit spacing, if we are going to decrease this, so we decrease wavelength. If we decrease wavelength, we should see a decrease in the fringe spacing. Okay, this is true. Okay, so in general, if lambda is decreased, then W decreases. These are directly proportional. So why is it that if we get to a specific value, meaning that lambda is equal to S, then it suddenly jumps up to be much bigger? That's because if we're putting in the wavelength to be different, it means we have a different source of light. Okay, and so that different source of light is going to have different amount of diffraction. We're going to look at this in the next video when we look at how would we do this with a difference between looking at lasers and now looking at white light, where we can have many different things. But if we keep this the same, it's a lot easier to change this slit spacing. So we can think about this another way. We can say that if we increase this slit spacing to be equal to this, as we generally, we decrease the slit spacing to be equal to the wavelength. As we generally decrease this, we have to increase the fringe spacing. Okay, so this whole question basis will usually be something like, if we increase the distance between the slit and the screen, how is that going to affect this fringe spacing? It's going to increase because the slit screen distance is directly proportional to the fringe spacing. If we were to increase S, it's going to decrease W. If we were to increase lambda, it would increase W. Okay, it's just proportionalities. Okay, so this has introduced your two equations and your applications of them. Hopefully this all makes sense. Thank you for watching.